Okay, so hi everyone, my name is Mikołaj and I will present to you my colleagues Mateusz Błajda, Kajetan Chwytyński, Aleksander Mysiak, and Marcin Chowski and Adrian Łańcucki. Our work with our supervisor, Marcin Możejko. The title of the work is Usage of Large Language Models from NLP for Training Prosody Models to Scale Up and Improve TTS Models with Large Datasets. So that's a pretty long title, so what does it mean? We are in the text-to-speech domain, so given a text we want to generate an audio of a person speaking. We want to leverage large language models to train the prosody. And now, what is a prosody? Prosody is basically how a person speaks. So a person can speak slowly or fast. It can speak with a higher voice or a lower voice. And yeah, that's basically the style of a person. It's not like a color of the voice, but it's a style of how people say. Yeah. So here we have a picture of of how different parts of data on the LJ speech dataset compare in the size. So we can see that the biggest square here is audio, and that's because the audio is like really dense. So for example, 10 seconds of audio contains 10 times, I believe, 22 or 44,000 data points. The smallest one is text, so for a 10-second audio it will be like a couple of words. And prosody is somewhere in the middle because it has information about the pitch and the energy and maybe duration of individual phonemes or graphemes. It's somewhere in the middle. Yeah. Yeah, let's define the problem. So nowadays, as we saw on the previous presentation, typically the text-to-speech models work in like two stages. So first is to generate the spectrogram from text, and then we generate audio from this spectrogram. Yeah, and the problem is that it is often the case that the audio must be of high quality. So it must be like studio quality, and it's really difficult to gather. Yeah, and the another problem is that okay, and how this relates to the picture that I showed before. There is not a lot of data. Like if we want to build a function that converts text to audio, we have like this small text, and we need to generate a lot of audio. So it's a really difficult task. So what we want to propose is to split this well generator to two models. So instead of going directly from text to spectrogram, we go from text to prosody, and from prosody to spectrogram. And once again, what is prosody? It's for example, pitch of a speaker in a given for a given phoneme and stuff like that. And why is it cool? It's cool because we got rid of the problem that the data must be high quality, because now when we see at this model, it does not touch the raw audio files or spectrograms. So it can be pretty much trained on sloppy data. So we can have like low quality data from some speaker in somewhere, and yeah, there's a lot of data that we can use. Okay, and however, the mail generation still needs high quality data. Okay, why is it cool? So As I said, the data. So there are lots of ISR data sets that can be utilized by our model. So it can because it uses it uses it's easy to use by our model. We can use multiple speakers to simulate their prosody. So, for example, we can have a person that talks really fast or slow or happy and sad. We can use an autoregressive model that is able to generate more variable data and thus generate audio that is more natural because it is often the case in text-to-speech models that if you generate a long sequence or any sequence, it is rather like monotonic and not fun. Thanks to the making the resolution of the data smaller, because as I mentioned at the beginning, the audio is really dense and the prosody and text is in the lower resolution. So we can just train on longer sequences and thus improve on like length of the generated sequences. So typically in the text-to-speech we have samples of in the order of magnitudes of like 15 seconds, and we can train TTS-LM model that generates 15 minutes sequences. And that's a bit technical, but we can use graphemes instead of phonemes. First of all, what is a phoneme? Phoneme is a głoska, I believe, from Polish. Pretty much the thing that you say, and the graphemes are what you write. And most of the text-to-speech models nowadays rely on phonemes. That's really problematic because you want to generate things from text, not from phonemes. And there are like rule-based algorithms that convert words to phonemes, but those have to be like constructed by humans or something like that. And an ideal text-to-speech would just consume raw text and audio. Okay, so here is a big overview of our pipeline. It's quite big, but don't worry, we'll get through it. So the green boxes are models that we are training, and we start with the scraper or just any source of audio data. Yeah, so given the audio data, basically what we want to do now is to extract the prosody, and then we'll train models on it. So let's extract the prosody. We use Pratt or Librosa to extract the pitch of the audio. Given ISR, we get the transcription of the text, and connected with MFA, that gives us basically alignments of the words. We aligned the transcript with the audio, so we know where the word ends. And then we train an aligner that basically aligns graphemes to the audio. And once we have all of that, yeah, because when we align the graphemes, we can assign duration to each grapheme. Yes, so that's our duration part of the prosody. Then we combine all of it, pitch, text, and duration. We input it to the TTS-LM that basically is a language model that models this stream of data. And then we input it to the complement model that outputs the spectrogram. And then we use standard TTS models like vocoders to generate the wave. Okay, so that's it.
Okay, so now I will talk about speech recognition. So the first step after we gather the data, the speech data, is to transcribe it. So we would have labels and yes, the axes and labels. So the problem with regular speech recognition models is that they doesn't recognize punctuation and capitalization, and we want our transcriptions to have those. So our first thought was to use Whisper by OpenAI, and Whisper actually detects punctuation and capitalization, and it's pretty good at generalizing. Yeah, but there's another problem with normalization. We don't want normalization, and normalization is, for example, exchanging the digits to the written form, to words, or, for example, shortening the units from kilograms to kg. And we don't want that. We want the words as they are spoken. So our goal was to find a model with punctuation and capitalization, but without normalization. And we found such a model. It's called Conformer CTC. With it has the version that supports our needs. So we use it as a first step in our pipeline.
Okay, so now that we actually have our transcripts, the next step that we need is the durations of each of the letters in the transcript. So as Mikołaj has already shown you, there is a tool that's called the Montreal-Post Aligner that actually just does that. It exactly does what we want. The problem is it works with phonemes instead of graphemes, and this wasn't what we wanted, so we decided to train our aligner, so a model that will provide us with durations of all of the letters. So we based our aligner on one that was presented in one TTS alignment to rule them all paper, and this paper gave us a pretty good start. However, some challenges still remained in the training process. So this is a task that's not very stable. Different letters can be spoken very differently by different people in different ways and so on, and so the training wasn't very stable, and it also required the use of very high quality data. So in order to make our life easier, we decided to use one of the outputs of the fourth aligner that we have mentioned, which is word level alignments. So from that tool, we got the starting and ending points of each of the words in our transcripts, and this allowed us to generate probability priors. So this is what we see here in the slide. So this is basically a probability matrix that expresses our belief as to which grapheme should be where in the audio without even looking at what the audio exactly is. So this is what we supplied to the model during the training, which was to give it a head start and to say, okay, so this is roughly what we're expecting. And it actually helped a lot. It stabilized the training, and it allowed us to converge the model and to use it to solve this part of the problem without many other issues. So, yeah.
And finally, to merge all of these streams that we created previously, basically text, which is described here as unit, duration, which is how long some sound is spoken, and pitch and energy, which is basically prosodic characteristics of our speech. We created TTS-LM, which stands for text-to-speech language model. We use multi-stream transformer that is based on Transformer XL, which is basically a transformer with memory module that we disabled for now, but in future works we'll probably turn it on to further improve our results. And combining streams is very simple. We basically create embeddings for each of the units that we created and add them together, resulting in 3 outputs that are units, 4 outputs actually, because this is the graphics from the paper that we were inspired by it, which is text-free and prosody of our generative spoken model. And we also use flash attention to optimize our reads and writes to disks. And we use prosody shift to move our prosody, like as you can see, the units here are a little bit shifted to the left, so we can combat the low quality data. And this model is highly scalable, so we can make this model to be much more large than it's in its original form.
Okay, and the last part of our pipeline is basically what's left. So we have the stream of the prosody, and now we want to generate the MER spectrogram. So in fast pitch, another text-to-speech model, we have normally on input we have a stream of like text, and it first works in the resolution of the text. So, for example, it's like we can think of it as a level of graphemes. It does some operations on it, then it upscales it to the resolution of the spectrogram frames that are, I don't know, it's about an order of magnitude higher, and it does some operations on that, and then it outputs the spectrogram. And what we do here is basically take the TTSLM. Oh, I should have mentioned it before, because fast pitch models the prosody inside of it on this level. So what we do here is we have a TTSLM that models the prosody. So all we have to do is to take this prosody, the text, and work directly on the resolution of the spectrogram frames and generate the histogram. It's cool because it's much more natural and easier to train, because fast pitch tends to be like really unstable during the training, and this makes it more stable. Yes. And now the fun part, where we have samples. So these are the samples generated by our pipeline with TTSLM and all the things, but we use for the spectrogram generation we use fast pitch, not complement model. We have complement on the next slide. And yeah, we have 4 speakers. We have some original data, original data from the speaker, the data from the training set, and the data from validation set. You'll see why it's funny later. And what we expect from the audio files is that the model will copy the prosody. So if someone talks like slow, it will the sample will be slow. All these samples are generated with the voice of one person, and all have the same text. So where's my mouse? Yeah, so I'll play speaker 1 and then the sample from the TTSLM.
I pointed to the new side of the cottage behind us. Is the cause there? I asked. No, no indeed.
Okay, sorry.
There is great no confidence in presenting this copy of its confession.
Yeah. One.
Immediately, intuitively, and infallibly discernible, and each fixed forever in whatever bit of experience it qualified. One does not see how there could ever have arisen any room for doubt or ambiguity.
I betray no confidence in presenting this copy of his confession.
Okay, so it sounds a bit weird, but you can hear that it does what it's supposed to be. So this speaker 2 talks like slowly with like I don't know, a grace or something, and the second sample here actually shows that. So maybe let's listen this to the fourth speaker.
How can you be so alarmed, Isabel? Of course I have, he continued in a peevish though kind tone as he took hold of her hands to raise her.
Okay.
No,
I
not
betray
yet.
no confidence in presenting this copy of his confession.
Once again.
I betray no confidence in presenting this copy of his confession.
Yeah, so it sounds funny, but we can see that it captured like the energy and everything from that person. And now we'll show the samples from the validation set.
Under these circumstances, and control of the art with granted within the political and
Yes.
under these circumstances, and told the with comprehension, we have been radical and slow.
Yeah, so we can see that the model definitely overfitted to the training set. However, it did what it's supposed to do, and we hypothesized that if we like make the dataset bigger, we'll be able to like generalize, because we trained it on Libri TTS, which is not a really large dataset. Yeah. So here are samples from the complement model, and these are.
The overwhelming majority of people in this country know how to sift the wheat from the chaff in what they hear and what they read.
Yes, these are better quality, but we do not have like the autoregressive model. The prosody model here is not autoregressive, so it was easier for model to generate the audio. But we can see that the complement can generate good quality audio. Yeah, and that's pretty much it, I think. I'll just summarize quickly. So we did a big pipeline for training text-to-speech models, and we are our pipeline is really scalable, and we are planning on training it on like internet data, and we hope it will work better in the bigger scale. Yeah, that's it. And yeah, so thank you.